Good evening, folks. Okay, so I think I've got roughly about 5 people out of our classroom that are here to go through our test paper. I'm going to leave it just for 1 more minute whilst people log in, because I think it's reasonable to wait till 6:31 just to make sure that everyone's in the place where they need to be. We've got 6 people. I think that's probably actually going to be about 5, but there's only 9 of us in the class, which means we're missing 4. I'll shout at them later. It's fine. Okay. So 30 more seconds and we'll start our webinar. What I have done, so what I'm going to talk you through is just number 1, talking through each question. You can see what I've done when I've filled out the paper. I have sat your exam. So I have done your exam in test conditions. I've gone through each question and I've answered this as if I was doing it. I've also then gone through the mark scheme in great detail. So I've made a note of all the various points where certain other areas or certain other answers would be acceptable. I've also looked at the percentages of each of the questions that have been done, and so we'll be able to give you an idea of which questions have been done badly throughout the class and which ones will have been done well. So, okay, what I'm now going to do is we're at 6:31. I'm going to put my glasses back on so I can see what I'm doing. So I'm going to share my screen with you guys. And then let's do entire screen. And then I'm going to click on this guy, get rid of that. Click on photographs, go full screen, flick through and go back. Okay. So I've taken a photograph of every single page in the test and I'm going to walk you through each one. The chat is running, so you are able to, if you've got any questions regarding it, I know Michael's going to have some. I am expecting them. I'll be able to help you out. I was going to write Mr. Duncan in the surname, but I thought I wouldn't. Okay. So question number 1. So first of all, we need to check off the multiple choice. Some of this should be fairly straightforward. Some of it's going to take a little bit of time. You'll see the notes that I've made. So, okay, they've given you, first of all, they've done the formation of an ester. They're going, but the trick to this is they're going from an ester to a different ester. Now, acylation, in terms of acylation would require you to be using an acyl chloride. None of those have been taking place. The second one is hydrolysis. Hydrolysis means breaking with water. There is no water in the equation. So C, substitution, would be a potential answer. I think a lot of students put substitution in their answer, thinking that you're substituting one group for another. Now, technically, that's not true. People think that you're subbing one alcohol for another, but because we're actually having the ethanol reacting with it, this is otherwise known as transesterification. We're creating an ester from an ester. The word trans, of course, means to change within. So it just means changing within the same family. So the 2 options there that students would have given was C and D, but D would be the right choice. I do understand the difficulty of substitution. Next one, vegetable oil, such as palm oil, can be hydrolyzed, the alcohol being produced. This was covered in my lessons under biodiesel. I explained very clearly. Now, just to point out, once again, the options are ridiculous. Propan-1-ol, never going to be the case. A diol, then the 1,3-diol, the one they're looking for. We know that vegetable oils are triglycerides. So we're looking for and the only trial option you had was 2D. Which of the following types of radiation can result in the direct breaking of bonds? So the only one with enough energy is ultraviolet. That picks up from FRS, free radical substitution. Infrared is heat. That's never going to be enough. Microwave, no. Radio, definitely not going to have the energy to do so. But ultraviolet, having the highest energy of all of those, is going to be the one that we're looking for there. Right. This question requires some explanation. So they had given you the graph of 1 over T versus ln rate. Can everyone see that it's a straight line through the origin? And they had been very generous, and they had reorganized the equation to match y equals mx plus c. Now, what I wanted to do is I wanted to walk you through the thinking of this. So I wrote down the equation again, then wrote down underneath that ln rate is going to be the y-axis. As you can see in the equation, the y-axis here is our y-axis. 1 over t is our x-axis. The constant, of course, is going to be the constant in the equation, so m must therefore be the gradient. And, of course, in terms of the equation they've given you was minus EA over R. Now, the next bit was you needed to extract minus EA over R, and then so I've extracted that out of it, and therefore translated that the gradient would equal minus EA over R. So now I can rearrange that new equation. That was the difficulty, trying to realize that you could extract a section and make it equal to m, hence gradient, is what a lot of the students struggled with. Now, what that meant is you then had gradient equals minus EA over R. You have to flip the sign of both. First thing you've got to deal with is that negative sign. You're going to flip both sides. EA over R becomes positive. The gradient becomes negative. Then you bring the R up and the brackets appears because you can't have minus gradient times minus R. So you want to bracket the gradient into that. So then, of course, it picks up as C. That was, for me, I thought that was a really interesting question. And it was the extraction that they were testing for there. Let's move on to the next one. Right, nice and straightforward. It then said there is a decrease in entropy in the system when. Right, we know that entropy is disorder. We are going from disorder to less disorder. We're going from messy to less messy. We're going from gases to liquids to solids. We're looking to decrease the mess. Gaseous molecules decompose into whoa, stop. Decompose into more gaseous molecules? That's going to be messy into really messy. Not going to be the right one. A solid decomposing into a gas, oh my goodness, no way. Solids are ordered, gases are disordered. That's going to be a massive increase in entropy. Vapor condensers, we're going from a gas to a liquid, you're done at that point. Solid to a liquid, solids melt, increase in disorder, going from solids, particles fixed in the lattice, unable to move around each other, to liquids where the particles can move, increase in disorder. So C was the obvious answer. Right, this one required a little bit of work. So, what is the enthalpy change for dissolving sodium chloride into water? Now, they'd given the equation of the solid going in. They then said the enthalpy of solution is enthalpy of solution, hydration is hydration. I have drawn the diagram which every one of you should have already memorized. mx solid going to m plus aqueous plus x aqueous. They already gave us it. But then, on the bottom of the Hess cycle, are the ions as their gaseous forms. Now, to be honest, this was not a difficult question, but you had to know one thing: lattice energy. Now, lattice energy is gaseous ions forming a lattice. Now, students often ask, why is it not, how do I know the difference between lattice energy and lattice dissociation? I never know which one it is. Right. In chemistry, we're making products. We're bringing things together. So unless they state otherwise, it's going to be formation. So that was the trick. And you'll notice my arrow here. So my arrow here is clearly going from the gaseous ions to the solid product. Now what that meant is you then did your standard Hess arrows this way equals this way. But this one is now going against you. So minus the lattice enthalpy plus the hydration enthalpies minus lattice plus hydrations, and it was D. So a tricky question, and the only test there was, do they know what lattice enthalpy is and can they create the cycle? Do you know what? For 1 mark and 1 minute, it's a tight one, that one. There usually tends to be 2 types of multiple choice, the really quick ones and the slightly longer ones. Well, this one seemed to fit right in the middle. Quite unusual, really. Right, next. Energy is given out when 1 mole of gaseous sodium is hydrated. Explain why potassium is more exothermic. Sodium chlorides are more soluble. What? No, makes no sense in context. First ionization energy is greater. Again, not in context. We're going from 1 plus sodium and 1 plus potassium. We're already ions. Lattice energy of first sodium compounds are more exothermic. Lattice enthalpy correspond to... They're waffling on about lattice energies, forming of sodium chloride and or sodium compounds and potassium compounds. It has nothing to do with hydrations. The radius of the sodium ion, and I've then gone into a little bit of an explanation. I drew out the sodium ion is smaller than the potassium. What this means is it has a higher charge density. So the bonds that are being formed with the water will be stronger. And if you form stronger bonds, if you form weak ones, you get a little bit of energy. You form strong ones, you're gonna have more exothermic, you're gonna have more energy released. So it's going to be D. Next. Nice easy question on KP. This one was lovely because two of the chemicals in the equation were solids, which means they can't take place in pressure anyway. Pressure only affects gases, which means the only one that's going to matter is oxygen. Its product, it should be products over reactants, so technically it would be products over 1, but 1 doesn't appear in the equation, so you can just have it to its stoichiometric ratio of 1/2, so it was going to be C. All the rest of them, that one, of course, is how many students thought that it was reactants over products. The D was the only other one which was going to be taking, that was going to be in the people's thoughts. Most people went for C, which was good. Right, this question was answered badly. The dissociation of methanoic acid in aqueous is endothermic. When the sample of aqueous is warmed, what happens? I have tried to do this in an equation. I've shown the ethanoic acid goes through decomposition. We know this. It's a weak acid. It's going to dissociate into the methanoate ion and H pluses. H pluses account for pH. And the forward direction is endothermic. Now, they've told you that in the question. They don't have to do that. We're breaking bonds here. We're breaking an OH bond in the oic acid. And if breaking bonds, mexobendo, making bonds is exothermic, breaking bonds is endo. So that forward direction is going to be endothermic. If I heat this up, I'm going to encourage, I'm going to break more bonds. So I'm going to push, so the H plus will increase. So the pH will decrease. That was a trap, that. But just to say, there was a pro on this one, which was the pH does not change. Of course it changes. pH of water changes with temperature. The concentration of undissociated will increase. If you heat something up, stuff breaks. So that's going to be ridiculous. Of undissociated increase? No, it's going to dissociate. The concentration of methanoate ion would decrease. That one was probably the choice that I think some people went for. I think what they'd done is they'd not realized that writing the equation there for the dissociation. That, by the way, this is the Bronsted-Lowry rather than the Lewis. If you have any questions regarding Bronsted-Lowry equations versus Lewis equations, please remember to ask me tomorrow. Next. Right, which solution has the highest pH? Guys, I was staggered by the number of you guys getting this wrong. And the highest pH is strongest alkali. Now, I know I shouldn't be using the word strong there because that's regarding dissociation. I should be focusing on the continent and who's doing what. And in this case, I've got, it's either going to be A or B by a mile. They're the only strong alkalis there. Ammonia, year 13, please take this as something you need to know. Ammonia is a weak base. It is only partially ionized. pH 12, you should be able to quote that. Really should. It's important. Really is. So it's either going to be the 0.01. Well, of course, if you have a higher concentration of hydroxide ions, you're going to have a higher pH. That one, I could go into a lot more detail. And if anybody wants me to show them how to use this, because, of course, if you want to work out the pH, you could have full-on used kW. I'm hoping that everyone in our classroom knows kW is 1 times 10 to the minus 14, 10 to the minus 14. So we should be able then to use kW to calculate the pH of that hydroxide solution. If you're not sure, please come and ask me tomorrow. Oh, I've skipped ahead. Next. Right. This one required a bit of thought. an indicator with a pH of 3.8 to 5.4 range is suitable for which titration? I drew baby graphs. Aren't they cute? Well, I know. So, and then what I've tried to do is label them. So A was over here. And A is nitric acid and ammonia. That's a strong acid. We all know in this room, we all know that nitric acid, sulfuric acid, hydrochloric acid are our strong acids. Yeah. Any OICs, any organics are weak. So this is strong acid, weak base. Heck, if you couldn't do number 10, number 11 was borderline impossible because you needed to realize that ammonia was a weak base. So you get this rather lovely sloped up on the way out. So what that means is A actually hit out straight off. Now I could have stopped here with the drawing of the graph, but I wanted to draw some of the others. So this one hits it. The 3.8 to 5.4 is low. It hits the vertical region on that graph. Whereas if you look at B is a weak acid and a strong base. Starting at weak acid, so 3, sloping up gently, high vertical region. Phenolphthalein is the ideal indicator for this. Phenolphthalein changes color with the high pHs 9 to 12. That's a perfect part for that vertical region. The next one was ethanoic acid and ammonia. I wanted to draw this out for one reason. You can't titrate C. You can't do it. Weak acid, weak base, there is no vertical region. Now, if they ask you for this question is, why can't you titrate ethanoic and ammonia? You would say, there is no sudden pH change. There isn't. There's no vertical region. What that means is there is no sudden pH change. So therefore, there won't be a visible change in color that occurs rapidly. No rapid color change. So you don't know where the end point is. Now D, now that one is a completely different kettle of fish. That has nought to do with pH. So you flat out ignore D. That's a separate titration looking at something very different. So we ignored D. Next. Right, next one was quite easy. Looking at the conjugates. So they've asked you for the reaction between concentrated nitric and concentrated sulfuric. This, of course, is mine. Guys, I'm hoping every single one of you is realizing that's from benzene. Yeah, and I mentioned this during the benzene lesson. I mentioned that we had two acids going in, but they both can't behave as such. Now, the sulfuric is diprotic. What determines whether an indicator is suitable for a titration or not? Great question, Jason. Going back to that previous question. Thank you for that, Jason. Right. Okay. So you should have done this with Miss Childs. Now, so a titration produces a rather lovely graph because let's just take the strong acid, strong base. That's this one here. You've probably recognized these graphs. The pH remains low throughout the experiment because you've got lots of excess acid. You're adding a base which is neutralizing it, forming water. Water has very little effect on the pH. So for the start of the reaction, the pH changes very little. And then all of a sudden, as you approach the point when the acid is used up, there is a sudden increase in pH. Now, this is called the vertical region of an acid-base graph. Now, during that vertical region, the pH changes rapidly. Now, if the pH changes rapidly, what that means is, in reality, the volume change, because this is, and I quote this is important, it is vertical. What that means is there is no change in volume of the acid between this pH, pH 3, and this pH, pH 12. So all you need is an indicator that can change color within this vertical region. It doesn't matter where in the vertical region it is, because if it changes up here, it doesn't matter because the volume change is 0. If it changes color down here, it makes no difference because from here to here, there is almost no change in volume. So your endpoint would be within 1 drop. Now, if you look at the graphs I've then drew, the strong acid starts at pH 1. and slopes up gently. And then there's a sudden increase as we approach neutralization, but because it's a weak base, it doesn't go up very high. It approaches the pH of around about 9 and then has a gentle 45-degree increase. The vertical region is low. Now, what this means is an indicator such as phenolphthalein, which changes at 9, which is at this region up here, would have missed the 0 volume change for the sudden pH change, which means your indicator will tell you a volume, it'll change up here, and you've added too much here. So you don't know that the correct endpoint. You think, if you used phenolphthalein for a strong acid, weak base, when it changes from pink to colorless, you've added too much acid and you've missed the neutralization point. So when I drew these graphs, now, just to tell you, I did this under exam conditions. I have not done this with the mark scheme, and I've then gone back and and then checked my answers and gone, yeah, okay. And you'll see some of the edits I've made. I like to do it this way because I want you to realize that as a teacher of 10 years, I will also make mistakes. And me making those mistakes is as valuable for you to understand, because although they're few and far between, it means the ones I'm making are the ones that are difficult. Now, this one, I had to draw my graphs. You should be able to sketch, like I have, all the... Do you notice that I've sketched all of them? I have done strong acid, strong base, strong acid, weak base, weak acid, strong base, weak acid, weak base. I didn't just do the ones that were given A, B, C, D. I just drew the lot because it takes 10 seconds to do it. And then what I did is I then said, okay, nitric acid, strong, weak, where am I? Looked at my indicator range and realized A was the right choice. These graphs you should be able to sketch, and it is important. It's something that you should practice. They're gonna come up heavily, so be aware. But by the way, Jason, thank you very much. Great question. If you want any further detail, I've got dozens of those questions that I can walk you through. So just come and see me. Next, so okay, we were talking about this idea of Bronsted-Lowry acids. Bronsted and Lowry, there are now 2 acid and base types that you now realize, thanks to Miss Childs, for both of them. Bronsted-Lowry are proton, acids are donors, bases are acceptors. So we need both of them to be proton donors. So looking at the start of the equation, the sulfuric acid is donating a proton to the nitric, hence forming the hydrogen nitrate ion, and it's gained one. So the sulfuric acid is acting as a proton donor, Bronsted-Lowry acid. Now, if you look at the equation in reverse, the nitric acid would be donating to the hydrogen sulfate ion. So this one can act as the donor. So these two are both Bronsted-Lowry acids, hence the answer D. Right, this one, I've given you a bit of a diagram. So when one of the optical isomers of 2-bromobutane, right, first thing, this needs translating. We've got one optical isomer. Look what I've drawn. I have drawn the optical shape. I've drawn it tetrahedral, and I've labeled it as L. Now, just to tell you, I don't know in matter of fact whether or not that's L or D or not, but it doesn't matter. They haven't specified which one they want. It makes no difference which one I draw. I just wanted to be able to give you guys a feel for what this looks like. Now you can see the slight edits I've made. So the optical isomer reacts with the hydroxide drawing an SN2. First thing is, God, SN2 requires clarification. I've done it with you in lesson, but it's not an easy thing to do. SN2 means that there are 2 species that are affecting the rate of reaction. So both the hydroxide ion and the 2-bromobutane are affecting it. So they're both involved. SN2 requires the hydroxide ion to attack. Now what this now means is, because it attacks it rather than going through SN1, which is a thermal decomposition to form the trigonal planar intermediate, I'm going to have the hydroxide ion attacked due to the polarity. And I will form an intermediate shown here. Here's my mouse showing it. This guy here, can I make my mouse large? No, I can't. Oh, I can. This guy here is a trigonal bi-pyramidal intermediate with a negative charge. A lot of you didn't spot that. But anyway, it's coming up in a later question. So I formed this intermediate, and it's trigonal bi-pyramidal. Now what that now means is, in the second step, the bromo breaks away. What this means is the transition state folds inside out, which means I will go from an L to a D during an SN2. I am still optically active. I have not got a racemic mixture. So now, can you see the mistake I made? The first thing I realized, I was like, oh, hang on a minute. SN2, there are 2 steps in the reaction, and I showed my diagram. Now, the diagram suggests 2 steps. This isn't correct. In SN2, can you see in my first diagram, I did hop on, hop off. Now, you draw that as an SN2 in a single diagram, but there is a very, very shortly lived transitional state in SN2. And that was the tricky. I crossed it out because I realized, whoa, hang on a minute. I'd drawn the 2 steps, but then realized that if I ran through, I didn't just end my thought process. I didn't see A and go, A, jog on. I went A, that's what I thought it was, and marked it. Then I said B, the butane 2-ol, which forms is optically active. And I said, yeah, that's true, because I know it's going to fold inside out and I will form only D, hence optically active. Racemic mixture was off the cards. I do not have a planar intermediate. That's SN1. But I realized that it was B, not A. Give me 1 second, folks. I'm just looking to find my mobile phone. Sorry, guys. I've got people asking questions. Sorry about that, guys. Okay, next. Right, another tricky question. Ethanamide, I like to say it, ethanamide is my way of saying it, is formed in 1 step by the reaction of, now you'll notice I wrote on this tricky, NAE, 2-step but fast. So ethanoic acid and ammonia, a weak acid and a weak base. Though that reaction there, although could potentially give you ethanamide under certain conditions, it's not going to. We've got an acid and a base. We're going to form ammonium methanoate. That's an acid-base reaction. The next one, ethanol alkaloid and ammonia. Now that one should have been screaming, folks. It should have been screaming, this is fast. I've explained to you guys that the ethanol, the O alkaloid, the ace alkaloid family is terrifying. It's full on quick. So that one should have been standing out. Ethanol with hydrogen cyanide. Now that's not true, because if you add hydrogen cyanide, you're going to go through nucleophilic addition, in which case you're going to form an intermediate, which is going to be the one with the cyanide group. My second laptop is just running out of battery. Bear with me for 1 second, folks, while I plug it in. This is causing me trouble. Sorry, folks. Give me 1 second. One second. Sorry, folks. Give me a minute. Give me 1 minute. Battery's fine. Sorry, folks. Okay, so the ethanol and hydrogen cyanide, you're going to end up with a hydroxynitrile and not the ethanamide. So that one's definitely not right. Methanol and methylamine, that's definitely not right. You're going to end up forming in all kinds of funny intermediates, because the ethanol, remember, is going to be acting. You've got 2 nucleophiles here, both of which have lone pairs. So they're not going to want to interact with each other. The only option would have been D. That was really clever, because everyone in the classroom should have been saying, but Mr. Duncan taught me NAE as 2-step. And it is a 2-step reaction, but it's really, really fast. And they wanted you to say what they didn't. The question was a trap. It's not 1 step, it's 2, but it's 1 reaction. You don't have to do any further process. I didn't like the question. I thought it was mean. So just bear in mind that they're saying things there. For EdXL to be doing this, folks, it's telling me something. It's telling me that the exam board are totally okay with manipulating setups and questions to make it seem a lot more complicated and to make people think, hang on a minute, I've been taught wrong. You have not been taught wrong. The question is worded to make it hard. Let's look at the next one. All right. Okay. Let's zoom in. Right, next one. An organic compound Y has the molecular formula, and it tells you some infrared spectrum data, 713. No broad spectrum here. Refer to pages 5 and 6 in the data booklet. Guys, how did you get this wrong? I don't know whether or not the data book has completely like freaked people out, but I'm hoping you didn't need to, because you didn't. Because the first options we've got is, look, there's only one oxygen. And it says the compound could be an alcohol, an aldehyde, and a ketone. Well, it can't be. There's no broad peak at the alcohol region. So it can't be that one. A is out the window. A ketone, but not an alcohol or aldehyde. Well, hang on a minute. At this point, it is possibly worthwhile, because you should have realized that 1713 was quite a high, which actually technically suggests it's high, which means technically it suggests an aldehyde, but it's still a really tight range. I'm half tempted to say that the chances it could have, the only two options you had here was C or D, but to have a strong absorbance at 1730, it's quite low in the 1700s. The data book says 1740, I think, to 1760 or something for the ketone one. So it was an aldehyde or ketone. It's a bit low. So it could have potentially been both. I thought that was a tricky question, that one. Can I just point out, by the way, I did that question, and I was looking at the data book, and I'm suddenly looking at it thinking, I still have a small amount of doubt within in that multiple choice of 15. So I'm happy to have a look at that one with the classroom tomorrow with the data booklet and see if we can come up with a stronger answer. I should have extracted the data and written it down, and I apologize that I didn't. Please, someone in the classroom, please flag 15 in the multiple choice as something for me to go over with you in lesson. Right, D, compound Z is an isomer of Y, has the structural formula. So they've told you this time it's a ketone. Guys, whoa, hang on a minute. Z is an isomer of Y? They've just told you that it's a ketone. Oh, it could still be 1, 2, 3, 4, 5. It could be pent. Well, okay, it could be pentanthreone. It could still stand, but it does suggest that Y is going to be, hang on, compound Z is an isomer of Y. It suggests that Y is going to be an aldehyde, but it's, anyway, I'm just suddenly, by the way, talk about looking through a paper and realizing there's an extra bit of sneaky data in there that's helpful. Right. High resolution NMR. It's given you the structure, it's asked you for the splitting pattern. Guys, I'm sorry. If any of you did this without drawing this out and drawing on the spikes, you're crazy. I had to do it. There's no way that I was going to end up getting that splitting pattern without drawing it out. So I drew it out and went singlet. End one by the ketone group on the far end, far right has got to be a singlet. No in non-equivalent hydrogens next door. This one's going to be a triplet. The original peak plus 2. This one's a nightmare. This one's 6. Original peak plus 5. People often forget that guy. That's what they don't do. Last one, original peak plus 2. So singlet, triplet, and a sextet, sextuplet. So the only one there was going to be A. 2 triplets, a 6, and a 1. So A was the answer there. Right, next one. Oh, I love this equation. It's my favorite equation. It makes me so happy. C1V1 equals C2V2. This is the dilution equation. And I cannot tell you that this is the most important, this is the most useful equation that you will ever take away going into your degree. If you do anything with science, this is the only equation in chemistry you'll use. It's the idea that you dilute stuff with water. So we're going from the original concentration of 1 molar, hence C1, 1, the original volume of 10. The new concentration is a question mark, new volume, which is the total, not 990, although the other numbers makes no sense anyway. Run it, rearrange it, 10 over 1,000 gives you 0.01, minus log it, and you get 2. Nice and easy there. Clever question. I love my dilutions. They're great. Right, next. Gas chromatography is only carried out at room temperature. That's garbage. Most of the time they have these things in big like ovens, keeping them the gas to stop it condensing. So that's garbage. It can be used to sample and which decomposes when vaporized. You've got to turn it into a gas. It would fall apart. B's garbage. C, it can be used for non-volatile substances. It's brilliant. I love lobbing solids into a gas tube because that's going to go really well. C is rubbish. D, it can be used to measure the amount of components in a mixture. The reason for that is it's going to be run through a mass spec after, which is going to measure the percentages in it, which you work from the ratio of the peaks. So it's interesting that one because in reality, D is not technically from the gas chromatography separates the component gases, doesn't measure their amounts, but that's done in the mass spec, which they're always funneled into at the end. Next, right, this one required a drawing. So I drew out the picture, dichloroethene, and I'm hoping everyone in this room is looking at my diagram and going, haha, Mr. Duncan, I think you mean Z dichloroethene. Of course you would be. You're all thinking that. I know this. But I drew it out. The reason being is it told you the bond I needed to break. So I drew it and lobbed a line through it. I was like, I'm chopping this guy off. What have I got left? I've got 2 H's, 2 carbons, and a chlorine left. That's because it told me I'm breaking that one. So what that meant is I then just added the masses up. 12 plus 12 plus 1 is 26. And then I said, what's left? So 63, which was the MR that they told me in the question, which was here, minus the 23, minus the 26, which was the only thing that carbons and hydrogens could be. The chances of having other isotopes are really, really slim. If you run the other numbers, by the way, it doesn't add up. And you get 37, which means it had to be D. That one, you could have spent an awful lot of time on and have got the same answer, but you've just evaporated all your time. 1 mark, 1 minute. There was a shortcut. Work out the others. Assume your standard isotopes. Carbon 12, 1 in 1,000. Hydrogen, like H2, deuterium, that's about 1 in 1,000 as well. These are rare. Chlorine's obviously going to be a common one. It's 1 in 3. So it was the one to go for. But again, it required a bit of an assumption. A lot of them do. Right. Last of the multiple choice. Right. You can see what I've done here, folks. They asked you to use the data booklet. So I turned to the data booklet, went to page 5 and 6, scrolled through it until I found the bit I needed. By the way, do you notice that it said 5 and 6, which was a totally like, you didn't need page 6. You just needed page 5. You found the one that you needed and it said aldehydes. Now, this comes back to my previous question. Aldehydes are high. Just to say, sorry, folks. I missed the 0 off there. Lol. Ketones are low. Now, this actually suggests that it should have been the aldehyde because I think it said 1720 or 1740 on the other one. Suggests not a ketone. But I know that. And then I said on my previous one that it was aldehydes or ketones. It was on the fence. So, and the previous question then suggested, again, I need to look at the data booklet and then we need to check that one out because I think that one's still a little bit wary. But this one, look at the peak. I zoomed in on the peak and I wrote on 1500, marked the 1500 point, then marked on the 16, then marked on the 17. This is clearly very strongly at 1750, which fitted in with the aldehyde group, which is even still, that's high. You're meant to be looking at 17. That's a little bit high, to be fair. It was pushing it right to the extreme end to make it far more obvious. So it was looking for you to say aldehyde. Only one aldehyde here. Enol. What? Enol? What? That guy doesn't make any sense at all. You've got no structure. That could be anything. Branched. There's not even any oxygen in it. What? The other twos. So it was the only ones to choose from were between A and B. But it was A because, of course, the peak being a little bit high. Right, we're on to the next bit. So, okay, these are the long answers. These are going to be a little bit more tricky. Can I just say, data book? The data book's a nightmare, especially when they don't tell you where the information is, scrolling through pages. But guys, right, do you know what I found? And I'm sure you guys have all found it too. If you haven't, oh my God, the content page on page 2. I was flicking through this book, going forever, and I was like, oh God, this is a nightmare, I can't find it. And then I closed it, opened page 1, I went, aha, entropy data. Yeah, and I was just like, okay, page 12, turned to page 12, extrapolated my data. So here's all the data from the data book. Magnesium at 32.7, chlorine at 165, that's a baby plus. The chlorine gas is far higher than the solid, makes total sense. Then we're going into an ionic solid, which is somewhere in between, because of course we've got multiple atoms here of different types. The entropy is going to be somewhere in the middle. It asked you for the entropy of the system, which of course everybody in this room goes spray, SP minus R, entropy of the system equals the change in entropy of the products minus change in entropy of the reactants, P minus R. I just tend to call it spray. The another one that another student said was super. I quite like super actually because it's the first, middle, and last letter. So super. Products, entropy is products minus reactants, but only for system. I ran through my numbers. It told me the bit I needed. There's the product of magnesium chloride minus the sum of the reactants, which are these two, and you got minus 108, which makes total sense. You're losing disorder. You're going from solid and a gas to a solid. And of course, the next question asked you that very question. Explain fully why the sign of... So if you didn't get this, you were full-eye stuffed for the next one. It then said, explain fully why the symbol change is what you'd expect it to be. You had to say for 1 mark, a solid and a gas. Oh, Audrey, are we not allowed to write minus instead of the calculation? Instead of the calculation, that's kind of what I've written. Are you saying that? Are you saying to ignore the brackets? Right. That equation you should always spit out, Audrey. It's one that you should have had drilled into you for system. You should just be like entropy P minus R and to run through it. And I'd always look for including the brackets for you because you need to explain that you understand that those are the reactants. You probably got the same answer, did you not? If you ran that number through, the problem is if you're not careful, you do it on a calculator badly. I did and got the answer right. Good. But not the working. Yes, that's fair enough. Just, yeah, be careful. What they're saying there is in the, by the way, I'm going to have this off Michael a lot, saying the fact that, well, if I got the answer right, I should get all the working. I'm very, very wary of this. If you're doing crazy things with numbers, I'd hope to think that I'm not trying year 13 to take marks off you. If you've got the right answer, and I will send you the legitimate mark scheme tomorrow, I'll post it on the classroom so you guys can look at when it says if they have this answer right, gain full marks. But I am very aware that me and Miss Childs are not trying to teach you how to spit out an answer. We're trying to teach you how to give a methodical method to make sure that when you get those impossible questions, you get them right because you've got a solid process in place. I'm sorry that if you feel like I'm being mean and not giving you the working marks, but just we're trying to encourage good working. So when you get those horrible ones, it makes it clearer, that's all. So, Audrey, I'm sure if you've got the right answer, I'm sure you probably would have got the 2, just so you know. Explain fully why the sign is correct. So, okay, I'm just going to scroll down on the question bit. Audrey, no, because I used the same values. Yes, potentially you did use the same values, so I assume that you would have got perhaps the working out mark. If you got the same sign, the problem is technically, I don't know what, I don't know. If I run that through a calculator, exactly as you've written it on that chat, Audrey, do you get the right answer? If you do, then I can't really argue it, to be fair. I'm, as I said, just trying to work on a method here, rather than, I've probably been overly mean. It's always best to be. Okay, so then I explain why it's expected. First mark for the expected bit. Got no more questions off Audrey, which is great. Explain why it's expected. So you're going from a solid and a gas. Now, gases are massively disordered. So you're going from so ordered plus crazy disordered to somewhere in the middle. It's going to decrease because gases, if you ever go from a gas to a solid, you're going to have a decrease in disorder. I hope Ms. Childs has made a big point of you are not allowed to ever say the word order. It is banned. Everything is done in regards to disorder. And you've got a loss of disorder here, and that's because your gas is vanishing. So you had to state for the first mark, solid and gas are forming a solid only. That was the key mark. Solids are less disordered than gases, hence you're ignoring the other solid. Who cares about the magnesium solid? We're talking about chlorine. Solids less disordered than gas, sign will be negative. The key thing there was for saying solid only is the product and solids are less disordered. You got the 2 marks. Next. Right. Nice, easy, straightforward question. Calculate the total entropy change. We all know that the entropy of the total is surroundings plus system. This is not complicated, didn't require much work. All you had to do, though, is you just had to extract the data. You had to realize that you were taking the one from the question at the top. How many people just didn't realize that that number was above? And then, of course, guys, I'm very sorry. Please, please, please be aware that the whole error carried forward. They don't like this anymore. If you've got that question wrong, they're really not going to, there'd be a mark for the equation, which you'll probably get saying this, saying, I know what this is. If you put in the wrong value here without saying that equation, you're probably going to lose at least one of them, if not both. So just watch out in terms of being thorough with writing down the equations that I've taught you. And what Ms. Childs has taught you as well. So nice, easy, straightforward question, that one. As long as you had question AI, okay, you were solid on it. Right, next. Another straightforward equation. Entropy of surroundings is minus delta H over T. They told you the temperature in the question of 298. You took the surroundings, you took the enthalpy, and all you did is, first of all, I did a rearrangement. They're asking me in the question, calculate enthalpy. Every step is shown. Here's the equation I've been taught. First of all, flip the sign. I need the minus. I hope all the mathematicians in the room can realize that the minus can be written as minus the whole thing. So I can flip the signs on both sides of the equation. Got to deal with the negative first. So minus delta S would equal delta H over 298. Then bring the 298 over, and you end up with minus delta S surroundings times 298 gives us enthalpy. We pull our numbers from the previous question, you run it through, and it does exactly what we like. So it's, by the way, and also, guys, people, one of the hardest things as a chemistry teacher is to get you guys to have a rough idea of the numbers you're expecting. The amount of people who write into these, that I got an enthalpy change of minus 28,000. This doesn't exist. You're looking for reasonable numbers. You know, I love when people talk about bond enthalpies. I say, guys, a bond enthalpy is anywhere near 400. If you're looking at 400, you're gonna be good. So just, it's a good thing to say. As you practice, you'll pick this up, and it's worthwhile. Keep doing the practice. Make a note of those important values. There should be a little book. Get a beautiful little book from what's the stationery shop called? Typo. Get a nice little pad from Typo that looks pretty, and write in it kind of numbers I should know, you know, or rough values for these kind of changes. It's worthwhile doing. They make your life so much easier, year 13, I promise you. Next, this question, this one, okay, guys, I took a shot in the dark. I completely understand why there's going to be a 50-50 in the classroom of who got this right. Q equals MC delta T. Everyone knows it. But can you please spot 1 mark? What this means is they've given you 1 mark because they've given you the equation. So why would they give you 1 mark for this calc? Because, guys, they've given you loads of data with different volumes and different moles. This was a nightmare. So how did I come to my decision? Right. I decided I've got 0.03 moles of magnesium chloride prepared by. Right. They told me I'm making this amount. That's the solid bit. Would everyone here agree? You can't make any more than that. That was in my head. I was like, if they tell me I'm gonna make this much, I can't make more than 100%. So that was in my mind. It then said is added to 51.5 centimeters cubed of water. And then it said 50 centimeters cubed is formed and the temperature rise was this. Now I was sitting there going, which one do I use? If I use 51.5 or 50, I don't know which volume they're wanting me to heat. Now here's the thing, they're adding it to this much water. Now, why has the volume dropped? The volume's dropped because I've added a salt to it, which will change the packing arrangements in the final product, which means its density changes. If its density changes, its C changes. The heat capacity of water, which is 4.2, and they had quoted 4.2, which made me want to use 51.5. Now, at the end of that, I was like, I could use either. However, because at the end of it, it literally put 50 centimeters is formed and the temperature rises. I took a shot in the dark and I went for 50. It turns out on the mark scheme, you can use either. It really, really annoyed me. In fact, I was furious at this question because in my opinion, if you've added it to that much water, that's what you're heating. I was really, really annoyed at that question. I took a punt and I went for 50 because it was on the line of the delta T. No other reason. I was in debate. It turns out on the mark scheme, they allowed both. So anyway, what that meant is there was errors carried forward on this one. So you got your first answer, but can I just then say, so you got either one for that value or the other one. So if I've marked you as wrong, please come and see me tomorrow. You could potentially gain marks on this question. So I worked out the joules. Please note it says energy in joules. Some students converted to kilojoules immediately and lost a mark. Just be aware. Calculate the enthalpy change of the solution of magnesium chloride. I wrote down my equation, which everyone in this room knows, which is delta H equals Q over N. First step, convert joules to kilojoules because Q must go in kilojoules because this is kilojoules per mole. So then I ran kilojoules through my moles, which was up here. And I then got, of course, my enthalpy change of minus 157.5. But here's the thing. Hang on. I had to flip the sign minus because the temperature rose. So it's exothermic. Lots of students forgot to flip. Just be aware of that. It's a common thing. They're going to do it at AS and A2. So just be aware. Right, on to the next one. Right, this question was hard because, guys, that cycle, oh, I'm so, year 13, they have literally walked you into a trap. Do you know when I saw that cycle, I literally went, ugh, I'm ignoring it and drawing my own. You should have learned a solution, an enthalpy of solutions cycle. And it is mx going to m plus x minus, and these are aqueous, then gases. And I just drew my cycle. And I added on my data from the data book that I had to go and fetch. Nightmare. Logged in all my data. And then I realized they were asking me for this enthalpy. So I had to do some rearrangement. This way equals this way. This one's so I wrote down the original equation. The enthalpy of solution, which they've given you, minus 157.5 equals minus this guy because it's against me, plus this guy because it's with me, it's going in the correct direction of my arrow, plus 2 unknowns because there's 2 chlorides. It was a nightmare. I then had to reorganize it. Now you'll notice, do you notice how I never change anybody in the bracket? Ever. I don't like to do it. You mathematicians and your, I'm just going to flip the side in my head. Don't do it. Don't do it, year 13. It's an easy thing to do and you'll stuff it up. You'll notice I never change anyone in the brackets. Oh, Jason, can we get printed data books for our use when we complete on our own, please? Oh, Jason, I've already done them for you. I'll give you them out tomorrow. They're already printed and waiting for you. I'll give them out tomorrow. I'm really glad that you reminded me because I'm sorry about this. I printed them about a week ago and I just forgot to give them to you. Sorry about that. Sorry. So anyway, moving on. But yeah, by the way, Jason, I did have you in mind. And I had all the class in mind. And when I started looking at all these questions, I genuinely was like, this is a nightmare. Like, they need to have these to practice with. So, yeah, they're already done. I'll give them to you tomorrow. Just remind me. I thought I'd zoom in on my rearrangement. I'm just suddenly looking at my, my laptop and thinking that it's not entirely clear there without zooming in and seeing the numbers. I never change anybody in the bracket. I'm just reorganizing for the major ones. I move this guy over to here, change the outward bracket sign to a plus. I move this guy over to here, change it to a minus, run it through, and I got minus 763. This is good. This is screaming at me going, you're correct. Oh, because it's exothermic. All hydrations are. Hydrations are going from gaseous, no bonds, to bound to water. You're making bonds. It's exothermic. Divided by 2. And I was like, oh my guys, do you remember I just said 30 seconds ago, how strong is a bond? It's about 400. Nailed it. It's right on the money. Right, next one. Lots of people made a silly error on this diagram. Draw the diagram of the hydrated. Who forgot their delta pluses on the H? It didn't matter how many you put around it, but what did matter was that your H's had delta pluses on. And lots of people forgot them. Easy mistake. Right. Suggest why the addition of anhydrous magnesium chloride to water results in an increase in temperature. 1 mark. Right. We need to do that one first. This is quite difficult because you have to compare the hydration enthalpies to the lattice enthalpy that you're breaking. The enthalpy of lattice formation, the bonds to water. Oh, Juliet, 20 AI. How do we get magnesium chloride? 2A. Oh, I can zoom back out. How do we get magnesium chloride? Oh, are you talking about the data book, Juliet? Is that what you're talking about? Whoa, I'm zooming in, zooming out. Sorry about this, folks. It's tricky, this. How, Juliet, 20A, oh, 20A part 1. Hang on, let me scroll back to 20A part 1. That's not working. 20A part 1. It's the data book, Juliet. And Juliet, this is why I had the same issue. I realized, she said, yeah. It's the data book. Right. So when I opened the data book, I started flicking through the pages, Juliet, looking for the data regarding entropy. And I couldn't find it. And then I just, she can't type, so I am her messenger. Oh, Jason. Well done, Jason. You're a legend. Juliet, you just need to create a channel. If you create a channel, it'll let you join the chat. The data book, on the 3rd page, when you open up the front page of the data book, there is a content page. And it tells you thermodynamic data, page 12. And you just flick to page 12 and it's there. Juliet, come and see me tomorrow. I will give you your data book with you guys. In fact, I'm going to give you all your data books tomorrow, which you all get to keep and practice using. And I can answer any of your questions from there on how to track down the data. Juliet, good question. I'll show you tomorrow how to find it. Flip the sign, back to here. Yeah. So, back to here. So, entropy of hydration of the ions is greater than the lattice enthalpy, so overall exothermic. But for question 4, the mark scheme mentions delta H positive or / hydrogen. Yes, Celine, it does. What that means is you need to show that the hydrogen is slightly positive. Are you saying on the mark scheme it says it didn't require it? Okay, Celine, I will partly agree with you, saying that if you put those little dashy lines saying that there is an attraction between the hydrogens and chlorines, that you are therefore suggesting that the hydrogen is slightly positive. I am not going to accept that, and you need to make sure that in those diagrams the hydrogens are slightly are delta positive. I understand that you're doing that, but just to be aware that oh, I got it. Cool. Hey, Juliet's on. Whoop whoop. Yeah. I understand, Celine, and I could give you the 1 mark, and the next time that question comes up and it says 2, you'll score nothing. So I'd prefer you to be doing that diagram properly rather than doing it as a shortcut and doing a bad diagram. It's bad practice. And I'm pretty sure that even on a marking day, if you'd done that on a real paper, I'd guarantee you that a good chemistry teacher who was marking this paper wouldn't have given it to you without the deltas. Without the delta positive on the H, you cannot form an attraction. So I want it to be there. It's me pushing you guys to be better chemists rather than cheating chemists. So I disagree with the mark scheme, and I'm pretty sure that the mark scheme I think you're looking at is probably hand-drawn, and I disagree with it. So just, yeah, anyway. Right, why is there a decrease in volume? Oh, guys, this was a nightmare. And guys, I was doing this in exam conditions, and I took a punt, and I got it right, which is, if anything shrinks in size, what does that tell you about what's happening? Particles never change. If particles are going from ions to ions, no change will happen for size. For something to decrease in volume, bonds are getting shorter. So when you add the magnesium chloride, which is in a giant ionic lattice, which is a balance between the attractive forces between oppositely charged ions and the repulsive forces between the similarly charged ions, you form a balance between the two, and ionic bonds are actually surprisingly large. So when you dissolve them in water, the ions form very short bonds to the delta positive hydrogen and the delta negative oxygens. So the bonds shorten, and the whole overall solution shrinks in volume. So they wanted you to make all you have. By the way, do you see that I kept my answers short? Because I was like, God, is there any change in the ions? Is anybody changing charge? Because usually, why is there a change in size? Because I've gone from an atom to an ion and he's lost electrons, which means he's going to shrink in size. But in this case, no ions changed, which means the bonds being formed must be shorter than the bonds being broken. That was an A-star question. That was, oh my God, guys, can you see the word suggest? That's hard. And do you know what? I wrote that down thinking I've missed something. I got it right, but that is hard for me. So don't feel bad about it if you got it wrong. Next, number 21. Explain one reason, explain one effect of an increase in pressure. God, guys, there were dozens of answers. The top, of course, was there's going to be an increase in rate. Yeah, we all know this. The rate's going to increase. Do not say the rate gets faster. Don't do it. Faster, slower, quick. No, they don't exist in chemistry. It's increased rate. So the rate increases. This is because, explain the effect. More particles per unit volume, the collision frequency increases, therefore more successful collisions. You could have also said there's an increase in yield. Now, guys, the only reason why this was allowed is that arrow there says unidirectional. They only gave this because they told you that the overall yield was 79%, suggesting that one of these was reversible. Didn't tell you which one. So you could have said the equilibrium would shift from left to right, therefore the yield would increase because you're going from 2 particles on the left or 1 particle of gas to 0 particles of gas. Therefore, you've got more particles on the left and on the right of the equation, so it's shifted from left to right to decrease the amount of gaseous particles in the mix. So that was also allowed. 2 options. Right, next. The overall yield is 79%. Calculate the mass in tons. Give your answer to 2 significant figures. I underlined it. The bold, not enough for me. I need to underline that because I almost forgot, folks. I wrote my answer, was about to move on and saw my underline and went, oh, it's 3.1. You lose a mark if you didn't do it. So first thing I said was the ratio all the way through is 1 mole to 1 mole to 1 mole to 1 mole. That means it's just a 1 to 1 mole ratio because it just goes from 1 to 1 to 1 to 1. There's no change anywhere. So mole ratio is 1 to 1. Work out the moles. I haven't worked out moles, of course. Everyone in this room should be thinking, that's not moles because you've put it in tons, not grams. No, but the answer is wanting it in tons. So I'm allowed to do it. It gives you that. Multiplied by my 79%, which is 0.79. If you prefer, I actually don't like doing that. I prefer to do divide by 100 and times by 79. But you mathematicians will hate me for that one. So I get my moles, which isn't true moles, but it's moles times 10 to the 5 or something. Grams over rams, reorganized, times by 180 gives me 3.06 tons. And people forgot to convert to 2 decimal places. Can we run through this again in class tomorrow? Jason. The whole point of doing this, Jason, was so I didn't have to use up time in lesson, and I don't mind using my evenings to do this with you guys. Can I just point out I am giving up my evening for you guys? I hope you appreciate this. And I know this takes a long time to do. But Jason, if you have any specific questions about if there's anything on the webinar that you don't feel like is answered properly, circle it, highlight it, put it in a sparkly box. Come and ask me about that one question. I don't want to waste time in class doing it. I'm happy to answer your singular questions and any others that you've got. I'll do the whole paper with you if you like, but hopefully that I can get most of this done here. So yes, I will happily do individual questions with you, Jason. Next, classify the reaction type in step 3. Suggest a suitable reaction type. Oh, Sarah. Sir, for question 5, the mark scheme says it's sufficient to put hydration of ions is exothermic. So why the temp increase, or do you think it's safer to just elaborate? Sarah, that's a really good question. In that previous question, I'm really glad you asked, actually, because it's actually a really reasonable one. I totally agree with you. This one down here. In reality, you can't just say that the hydration is exothermic, because if you actually put about, I can't give a percentage and I wouldn't want to. Some salts, when you just, right, they're going to flip it, Sarah. They're going to give you ammonium nitrate. And they're going to say, Steve puts ammonium nitrate into water and the process is endothermic. Explain why. 2 marks. And you need to say that the energy to break up the lattice is greater than the energy released when the new bonds with water are made, hence hydration ions. Now, because it took more energy to break it up than released with the new bonds, the overall heat change will be endothermic. The fact that this happens to be an exothermic one and they don't mind you being, that's because it's a single mark. I'd be very, very careful. You should always, if someone says, why do you put salt into water and it heats up? You must always compare the lattice enthalpy to the hydration enthalpies. It's bad chemistry to not to. And this is what makes these tests a little, they're not perfect. You know, in my opinion, that answer's not enough, because it's always that all hydrations are exothermic, but not all salt dissolving into water is exothermic. A lot of them are endo. I'm happy to elaborate on that further. I can do this better one-to-one anyway. So I'm happy to come back to that one. Right. They then asked you for the reaction type and suitable reagent. Right, guys. Reaction type. Please, please, please make sure that if they say reaction type, you're not giving a mechanism. You're giving a reaction type. Esterification is a type of NAE, but it's complicated. So you put esterification. Yeah? If they ask for the reaction type of, I'm trying to think of another good one. Oh, nuts. Hydration. Hydration is a type of nucleophilic addition. And so I need to make sure that you guys get, sorry, not a great answer. There's the difference between a reaction type, acid and base, and a mechanism. There's only 7 mechanisms. Try not to quote a mechanism in the reaction type. Reagents. By the way, I went to town on the reagents. Ethanoic anhydride is the one they use in industry. Top answer. Ethanoyl chloride could be used, but it's explosive, so it tends to explode, so not used. Ethanoic, if you choose to do esterification with an oic acid, you must include conch sulfuric acid. Lots of people just wrote ethanoic acid, lost it. Be careful. The other ones don't need a catalyst, but ethanoic acid does. Right, let's zoom back out and go to the next page. Right, this easiest question, I think, on the paper. Stage 1, he's added coffee to a solvent. How do you get the oil out? Filter out the coffee solid. Just filter it. Stage 1, filter out the solid coffee grounds. Stage 2, you've got an oil floating on a solvent. Just fractionally distill it to separate 2 liquids of similar boiling points. You fractionally distill off. Yeah, by the way, that's not of, that's off. It's me being an idiot. Fractionally distill off the oil. You're done. Easiest question on the paper. Tricky one, biodiesel making an appearance. Propane 1, 2, 3 trial, followed by 3 molecules of the biodiesel. Catalyst, just so you know, the catalyst is KOH, but they allowed you to actually put in sulfuric acid, even though it's not used in reality. Doesn't matter. It's good. You're doing, by the way, this is transesterification, alcohol replacement. And as I said, you can use a conch acid or you can use KOH, either one. KOH is the correct one, but I was happy with the other one. Right. Oh, guys, how science works. What a nightmare. So, right, I need to make sure, year 13, I have one task here, which is I need you guys to realize, A, these questions are going to be there. They're going to put these, do we lose marks for not putting the H in the diagram? Not putting the H. What do you mean, Juliet? Do you mean on the C's? Is that what you told? Did you just put sticks? Juliet, if you're in an exam, you must show all H's in diagrams. You must. You have no choice. This is not practice. This is a real exam. Do you notice that on the trial? Oh, are you saying if you put CH2, CH, CH2 and doing like that? It just says complete the equation. It doesn't ask, yeah, fair enough. Juliet, you're absolutely right. It doesn't ask you for displayed. Did you show the bonds between the C? If you did, then you can have it. And I can happily give you an extra mark there. I'd recommend you to draw it out in future. But Juliet, come and see me with that. Circle, star that question, Come and see me tomorrow and I'll tell you whether or not it's allowed. Next. Right, yeah, back to this crazy one, how science works. Right, do you see how I've laid out my answer, year 13s? I have gone coffee oil, pros, cons. Yeah, and I've given one for each one. Renewable source of oil, coffee plants. Right, year 13, please don't be cheap in your exam. Do not just write 3-word answers. Please, 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 year 13, don't throw away 3 marks. These are the easiest marks on the paper, and they were thrown away by everybody. If they ask you to explain why it's good and bad, tell them why it's good and bad. Take some time. Look how much I wrote. Pro, renewable source of oil. Coffee plants continue to be planted. Yeah, you can just replant them. Con, only 10 to 15% oil from the mass. So large amounts of coffee bean will be required, resulting in possible deforestation. Palm oil, pro, it's renewable. We get it from trees. Plants continue to be planted. And also higher oil percentage. Con, large plantations, crops being grown for biodiesel, not fuel. Do you notice? Some people would now go, whoa, hang on a minute. They're both plants. Why haven't you just said resulting in deforestation like you did in the other one? I didn't like the overlap. Did you see the extended addition? They actually allowed both for the pro, but not for the con. They want, which, by the way, for me is inconsistent. And guys, that's the examiners being rubbish. You've got the mark scheme sitting in front of you, which of course has come from Michael. Thanks for sharing it, Michael, by the way. I do appreciate that. You're taking the effort off me. So the crops being grown, I just went for a different one. I didn't want, I'm sure everyone realized you could have been repeating yourself for the 2. But then I also just tacked on saying, they asked me in the question, consider one advantage of each source and which oil may potentially be greener. They wanted me to give alternatives. So I then, of course, tacked on palm oil is a better source. So those questions, guys, they're going to be there. Please don't cheat. Don't be cheap. Give it the time. 4 minutes. Break it up. You don't need to do this as a continuous paragraph. You're bonkers to do so. Please, please don't. Break it up. Make it easy for the examiner. They will love you for it, year 13, I promise. Right, number 23. Into rates. So, reorganization of the rate equation. Input my data. Nice and easy. That should have been pretty straightforward. Can you also see then my unit equation? Moles per dm cubed per second for rate, moles per dm cubed for the bromoethane, moles per dm cubed. Cancel those 2, bring it up, flip the sign, unit makes an appearance. Next, calculate the initial rate. I just plumbed in the numbers. Change it for 0.02. So I did. I just changed them both. Changed 2. Not increase, not decrease. We're just going to fix those. Spit out the number. So I did. Not complicated. Required you to get the right K value, of course. Error carried forward was potential. State the order of reaction. 2. Why? Because that's a 1. That's a 1. The overall order you add together. Overall order is 2. Transitional state. This had appeared earlier in the paper. SN2. You form the mechanism of the reaction can draw the transitional state for this. It's SN2 because, now people go, how do you even know that? Because guys, in the rate equation, 2 particles affect the rate. If this was SN1, the only one that would appear there would be haloalkane. And the reason for that is because the hydroxide ion would make no difference because it can't attack the species due to the reduced delta positive from the pi effect, which means it wouldn't appear in the rate equation. So it would only be an SN1 reaction. Now, because it's SN2, you form the trigonal bi-pyramidal intermediate. It's tricky, that, guys. That was hard, that. Move on to the next one. Let's go on to the next question. Input your data, plumb them through. Guys, now just to tell you, for this question, I did a rather neat trick, which was when it asked me to do this, it was just as simple as here's the temperature, do 1 over temperature. So I did it. But before I did that initial calculation, I did 1 over T for that number to check I got that one. When I did, I was like, winner, 1 over 333 gives me that. I did the same thing, LNK, because year 13, there are still issues with people not being able to use calculators. So I did on the calculator, ln, and inputted that number and got minus 6.6. So then I did ln that number and got that one. So I knew I was on the right lines. It's always good to run numbers that are already there because it confirms your methodology. Always a good shout. Right, guys, I am very sorry. I have not plotted the graph. So tomorrow, do I have you guys tomorrow? Let's find out. I have you guys tomorrow, period 5. I am going to do this graph question with you guys and explain that you don't need to do the wiggly lines and that the data is horrible to plot, but I'll do it with you. I have done a little bit of graph drawing with you guys, so can I just say, universally through the classroom, you guys did this pretty well. I was really, really pleased overall, so well done for that one, but I will do it in class anyway. Right, KC, this was a nightmare. Right, the expression, that was easy. These ones weren't. The enthalpy change is very small. That's the first thing I picked up. I realized, can I just point out, do you know all the rest of the question is totally unnecessary? Considering the effect of temperature on entropy change suggests why the change in temperatures have a little effect on the equilibrium. If the enthalpy change itself is very small, there will be very little effect on the equilibrium's position. So this one here goes with this point here, which is if the enthalpy change is very small, Kc will only change slightly. But then they wanted you, so you could have got 2 marks without even considering entropy. But what you then need to do is then spit out your equation. The enthalpy of the surroundings is minus delta H over T. And you realize if the enthalpy change is small and the temperature change is large, that value is tiny. So you're not going to make much difference. So that was can I just point out, in my opinion, stupid question, making you do stuff there which is completely unnecessary. If you've got any other questions regarding it, I'm happy to show you some other ones. But it's a stupid question, in my opinion. Right, one of the hardest questions on the paper, year 13. I have done my best to walk you through it. Right, I'm going to take my time on this one, 6 marks. First things first. They wanted you to react ethanoic with ethanol and make an ester. I wrote the equation, and it is a 1 to 1 to 1 to 1 mole ratio. 2 moles on the left, 2 moles on the right. The reason why I'm making an emphasis on that is because I'm gonna come back to it. Right, starting moles. They told us in point number 1. Starting moles were 0.12 for oic, ethanol 0.22. Notice how I extracted my data for my acid catalyst. Yeah, 5 centimeters, 1 mole. And then I put moles of water, 0 ester. Right, the mixture was left to reach equilibrium and titrated. Right, the titration will find the leftover acid, hence ethanoic acid, and the acid catalyst. Ignore my stupid diagram, I was getting bored by this point. So I had my acid catalyst, which means I can now run my moles of sodium hydroxide. 1 times 4.45 over 1,000 gives me that. That is the total acid. The total acid minus the acid catalyst will give me ethanoics. So I do that minus that, which gives me 0.04 moles of ethanoic. That is the acid left over, not the change, which a lot of you did. That's the acid left over. So the change is 0.8, 0.8, 0.8, 0.8. That one's lose it, that one's lose it, that one's gain it, that one's gain it. Add them all up. You can now input those values into KC and spit out a Kc value of 5.11, no units. And then, of course, said, explain why you can use moles. I think it's the next question, actually. Explain why you can use moles in this equation, because it's the moles are what's equal on either side, so the volume cancels, just so you know. Next, empirical formula. This one's nice and easy. 2 marks, 2 sets of data. Use all these data. Run your empirical, 4 to 10 to 1. MR, folks. Everyone missed it. 4 carbons plus 10 hydrogens plus 16 gives me 74, which was up there. Confirms. Draw the structures. If you have a problem drawing those isomers, I'm not going to be able to do it in the webinar. You need to come and see me. It's not complicated. I've got the hiccups. Do apologize. Come and see me about that. But this was butan 2-ol, butan 1-ol. Can't move it anywhere else. If you move it to there, it's still 2. Then add a branch. Lots of people drew the same thing. They didn't put that on the middle carbon. They put that one onto that one, which meant, of course, they're drawing the same thing. So just watch out for that one. Next, fragments. You just had to make 45. And those are the only fragments it could be. Yeah, 2 carbons, 5 hydrogens, and an oxygen adds up to 45. You couldn't get it any other way. So then you had to look at the other alternatives you could get. It was just a rearrangement of those particles, which meant it could only be alcohol 1 or alcohol 2. Because if you go back to here, fragment cracks here, see that. Fragment split here, see that. You can't get 45 from these. You can't do it, which suggests it can only be alcohol 1 and 2. And then, of course, just attach on your chosen pieces to form your ester. The organics bit on this was the easiest part, year 13. If you need some help with it, bring it to me and I'll do it with you. Guys, organic chemistry for A2 is puzzles. They require you to look at the questions, decide if you can do it, and then come and find me. And I'll walk you through them, which will be what I don't want you to do, year 13, is to do all these questions and get them wrong, and then to have bad technique right up to exam. Don't do them. Come and see me. I can fix it. I can fix it. Just make sure that you come and find me with them. You need to be practicing. It's important. Next, I think we're on the last question, are we not? It gave you a graph and said, draw the structure. You drew it out and it asked you to, so first thing was draw the structure for 1 mark and explain the splitting. So you can see how I've done it. Now, what was interesting about this question for me is I couldn't jump to that straight away. I had 2 choices. So look what I've done. I did them both. I drew them out and I looked at that one's going to be a singlet. This one's going to be a triplet because original plus 2, original plus 4, original plus 5, original plus 2, singlet, triplet, pentuplet, sextuplet, triplet didn't fit the split pattern, but this one does. These are puzzles, year 13, and they need practicing. And I just want you to be aware of how important it is. I will spend the time with you. You know, I have just spent the last 2 hours going through this paper with you this evening, and it's because you know how much I value doing this with you. I will give you any break time, any lunchtime. Come and see me. You know that. Guys, we're at the end of Unit 4. That's it. So if I just click exit off this and go back to here and click, I don't know how to get it back to, hey, hello, year 13. Oh, guys, thank you for getting through it. I hope it was useful. It's fully recorded. You can review this as many times as you like. Please, please, please pick up those points I made and which questions were tricky. Come see me. Come to me with the papers. I'll look at them with you. Otherwise, I hope it was useful. Oh, and I will see you guys tomorrow. See you later, guys.